Hello, everyone. Today I'm going to talk about sublinear time algorithms and complexity of approximate maximum matching. My name is Mohammad Roghani. This is a joint work with Soheil Behnezhad and Aviad Rubinstein. Uh, Matching is a set of edges that do not have a shared endpoint. So here in this graph, set of the red edges is the maximum matching of the graph. Our goal in this paper is to estimate the size of the maximum matching in sublinear time with respect to the size of the graph G. So basically, we are interested in the running time that is slightly better than quadratic running time. So n22 minus some constant. Also, we want to maximize the approximation ratio. So there's a trade. So we are interested in the trade-off between the approximation ratio that we can get in the sublinear time. In this paper, we use n as the number of the vertices, m as the number of the edges, delta as the maximum degree, and mu of g as the size of the maximum matching of graph G. So when we are talking about sublinear algorithm, it's important to fix the model. We study both adjacency list and adjacency matrix model in this talk, in this paper. In the adjacency list model, you can query the ice neighbor of vertex v. Each vertex has a list that shows its neighbors, and you can query the ice neighbor, and also you can query the degree of the vertex. In the adjacency matrix, you can query if there exists an edge between a pair I and j, and the oracle will return the status of the edge between, if there exists an edge there or not. The trivial approach is to make theta of n squared queries and construct a graph and then run one of the maximum matching algorithm to get the exact matching. It turns out if we are interested in finding edges of any constant approximation for the maximum matching, we need to query n square edges. So the trivial approach is the best you can do if you're interested in finding the edges. So we settle down for estimating the size of the maximum matching. So the question is what we can get when we are interested in the estimating of the size of the maximum matching. So if we care about multiplicative approximation in the adjacency list, we can show that omega of n queries is needed. Also, for multiplicative approximation in the adjacency matrix, we can prove that omega of n square queries is needed. The reason for the two previous statement is that if you have an empty graph G1 and a graph G2 that has only one hidden edge, in the adjacency list, you need to query degree of almost all vertices to find that edge. And in the adjacency matrix, you need to query omega of n square edges to find that hidden edge. So if we consider some additive error, in the adjacency matrix model, you need still omega of n queries. The reason is that if you have an empty graph and a graph that is randomly permuted, that has a perfect matching that is randomly permuted, you need to spend omega of n queries to find at least one of those perfect matching edges. Also, we can show that the number, if we are in the adjacency list model, the multiplicative additive approximation needs the average degree queries, which is if the average degree is equal to n and the graph is dense, still we need omega of n queries. In this talk, we consider only adjacency list model, and we also assume that the graph is dense. Hardness and Rose first obtain a half approximation algorithm in delta to O of log of delta. Monak and Nguyen in Fox 2008 improved the running time to O of delta. Yoshida, Yamamoto, and Ito improved the exponential dependency to delta and make the algorithm to run in O of delta to 4. Behnezhad in a breakthrough result got a half approximation in O tilde of n. Recently in the last SODA, Behnezhad, Roghani, Rubinstein, and Saberi beat the half approximation ratio with a slightly with a spending of n to 1 plus epsilon. That's slightly worse than linear time. So note that if we consider all the previous work before the paper by Behnezhad, if we let delta to be equal to n, like the graph is dense, none of the previous works are sublinear anymore. So only the last two works are sublinear for the dense graphs. So algorithms are getting better and better. So the natural question is that what's the limitation of the algorithm? Can we get, say, 1 minus epsilon approximation in linear time? Such an algorithm will result in a breakthrough application in dynamic algorithms. So because of the connection between the sublinear matching and dynamic matching, we can show that such an algorithm will result in 1 minus epsilon approximation with O tilde of 1 update time for dynamic matching, which is a breakthrough result in the area of dynamic algorithms. Our first result is that if we want to get a better than 2/3 approximation, we need to spend at least n to 1.2 queries. This is the first superlinear lower bound for this problem. All the previous lower bounds are omega of n. On the algorithmic side, we show that there exists an almost 2/3 approximate estimate of maximum matching in slightly better than n squared time for general graphs. Bhattacharya, Kiss, and Sanrak in a concurrent work got the same results in the same STOC. Also, we proved that it's possible to beat the 2/3 approximation ratio by some constant in a slightly better than a squared time for only bipartite graphs. This theorem 3 shows that our lower one cannot be improved all the way up to n squared. We start by giving the key intuition for our lower bound. So since this is a superlinear lower bound for this problem, there are some challenges. For superlinear time, in superlinear time, the algorithm will see some max matching edges. So we should make the yes case and no case in the hardness of approximation such that the max matching edges to be indistinguishable, because the algorithm will see at the end some of the edges, some of the max matching edges. And also because of the hardness of approximation, our yes case that has a large matching and the no case that has a smaller matching should be far from each other. So the max matching edges will look globally different in these two cases. So for example, consider a clique that has some singleton edges connected to it. So for this case, they are far from each other. In the left picture, the size of the maximum matching is large, and in the right one, the size of the maximum matching is half of the left one. But the max matching edges are easily distinguishable because one of their endpoint has degree 1. So we cannot hide those edges from the algorithm. And also because we have superlinear time, the algorithm will see some of those edges and can distinguish if they are max matching edges. So we start by building our construction step by step with some fail attempt. So suppose that this is our yes case, that it has a perfect match, all the vertices are matched. We have a perfect matching between SB vertices and also between BB and between AA vertices. For our no case, instead of having AA and BB perfect matching, we have a perfect matching between AB and perfect matching between the other AB. So the size of the maximum matching is 2/3 of the maximum matching of the yes case in the no case. Also, in all our construction, assume that there exist epsilon and dummy vertices that are connected to all vertices. These vertices are necessary for the adjacency list model to hide the actual construction. And also we assume that we have the S vertices for free. So if you query vertex, you will know that it's a S vertex or not for free. Now consider these two yes and no cases. So there exists an algorithm that easily distinguish between those two cases. So the algorithm will check if the graph has a path of length 3, and this task can be done easily in the sublinear time. So this is not the construction that we want. So we made a little change to this construction by adding a deregular graph between AB gadgets. So when we add these deregular graph, then the length 3 test is not working anymore because both cases have the length 3 passes. Now consider this algorithm that start a random walk of odd length from a vertex. Now in the no case, all those passes will end up in B because of the parity of the parts. So when you are in B, you will go to S or A, and then from S or A, you will go to B. But if you are in a yes case, when you start from S, you might end up in A because of the BB edges. So this task also is easy to distinguish in sublinear time. So we need to change the construction a little more. We add some epsilon d regular graph between BB vertices in both yes case and no case. Now this epsilon d regular graph will break the parity algorithm, the random walk algorithm. But now consider a random edge and estimate the degree of both of its endpoint. For AA edge, the degree is different from BB or AB edge. So if you're in a yes case, we can easily distinguish that. So we can sample several edges, and for each of them test if they are AA edge or not. And because we have superlinear number of queries, it's easy to distinguish between these two cases. So suppose that we add some extra vertices to both SB vertices in both yes case and no case. The reason that we add these vertices is to make the degree of the B vertices and A vertices similar. Now, with this new construction, we don't have any algorithm that's that's distinguish between a yes case and no case. But the challenge is that how we can analyze any algorithm, how we can show the limitation of any algorithm for these two cases. There are several challenges. So the algorithm may be adaptive because, for example, the algorithm will see some of the edges, and based on those edges, it query new edges. And also, the algorithm is going to see some of those AA edges. We have N2 1.2 queries. So the algorithm will see, for example, N2 0.2 AA edges because we have N of them. And so we have to hide those AA edges from the algorithm, and it shouldn't be able to distinguish which edges are AA edges. Now that we have the construction, let's see some of the key ideas that we use in our proof. So suppose that D is equal to N2 0.2, Q is less than or equal to N2 1.2, minus some small WAP1. Q is the total number of the queries that the algorithm makes. Because of our choice of D, and also the fact that we have epsilon and dummy vertices, each queried edge, and also the fact that the adjacency lists are permuted randomly, each queried edge has no dummy endpoint with probability of D over N. So our first lemma is that the result of the query that the algorithm makes is a forest. So we basically the algorithm will never see a cycle in the base construction if it has Q queries and Q is less than or equal to N2 1.2 minus O of 1. The reason is that, so the number of the edges inside the base construction is going to be Q times D over N, which is less than or equal N2.4 minus small O of 1. By the number of the edges inside the base construction, we mean the number of the edges that has no dummy endpoint. Also, the number of the pairs of the vertices with degree larger than 0 in the base construction is going to be N2.4 times N2.4 minus small O of 1, which is less than or equal N2.8 minus small O of 1. And we know that the probability of having an edge between each pair is O of D over N. So the total, so the expected number of the cycles in the queries is going to be much smaller than 1, so we don't see any cycle. So we can assume that the queries that the algorithm makes is going to be forest. Now suppose that the edges discovered by the algorithm is a rooted forest, but from U. So here U queries Z, U queries V queries X, and this is a long pass. And also this is our construction. So label of U, suppose that U is not an S vertex because we know a S vertex for free. Suppose that U is A or B, so we know that U is going to be uniformly A or B. But label of V is also uniformly between A and B, but it's highly correlated with label of U. For example, if U is going to be A vertex, then we know that V is going to be a B vertex with high probability because of this gadget between A B vertices. Also, the label of X is correlated with label of U, but it's less correlated comparing to V. So consider this long path, then we know that the voice correlation with U label is going to exponentially decay with length of this path. So we know that, so based on this fact, we know that those edges, those vertices that are far from each other are not correlated with each other that much. So, and the last thing is that we cannot concentrate many queries around A vertices. So suppose that UV is an edge between the A vertices, and TV is the subtree of V in our queried forest. So we proved that the subtree TV has few closed vertices. The intuition is that when the algorithm cannot distinguish AA edges, it cannot concentrate its queries around the AA edges, and hence it cannot learn to distinguish those edges by induction. So recap to our construction, we have yes case and no case. The yes case has almost perfect matching. The no case has a matching that has size 2/3 of the yes case. Our final solution is going to be the yes case with probability half and no case with probability half. The key ideas that we use in our proof is the reduction to the forest. The queries that the algorithm C is going to be a forest. The correlation decay on the long passes, the vertices that are far from each other in the tree are not important to each other, and the labels are independent. And in the end, we show that there are few queries around AA edges, so we cannot learn about those AA edges. And it leads to our final theorem for the lower bound. For the rest of the talk, we will focus on the algorithmic results. We had one 2/3 approximate algorithm in slightly better than a square time for general graphs, and also 2/3 plus some constant approximate estimate of the maximum matching slightly better than in a square time for bipartite graphs. So let's discuss some of the useful tools in our algorithms. So our algorithm has two main building blocks. So the first one is edge degree constraint subgraph called EDCS. It was first introduced by Bernstein and Stein in 2015. It used a lot in the context of dynamic matching and streaming matching algorithms. For a parameter beta larger than 1, a subgraph h of g is beta EDCS. If for each edge that are inside the, or each edge that is inside the subgraph h, the sum of its degree in edge is less than or equal beta, and for edges that are not inside edge, the sum of their endpoints is larger than or equal to beta minus 1. Therefore, the max degree of the EDCS is going to be beta because of the first property. Also, it is well known that the EDCS contains a two-third approximate matching. So consider our construction for the lower bound. So here, if degree of the vertices in A and B is equal to half of beta, and also SP edges are included in the EDCS, then EDCS does not contain the AA edges, so it's the two-third ratio is tight, and the EDCS cannot does not include the AA edges in our construction. The second useful tool for our algorithm is the fast LCA for matching on low degree graphs. LCA is the local computation algorithm. It was introduced by Levi, Rubinstein, and Pignani in 2015. So they gave a 1 minus epsilon approximate LCA for maximum matching in delta to 1 over epsilon cube running time. In the LCA model, we can query a matching status of a vertex, and if we query all the vertices, the results should be consistent to each other, and the algorithm should return the matching edge for that vertex if it's matched. Now let's see our two-third approximate matching algorithm. In the step 1, we sample slightly less than n square edges and construct a beta EDCS on the sampled edges. We call them edge. So the max degree of this constructed subgraph is going to be at most beta. Let U be the set of unsampled edges that does not satisfy the second property of EDCS, say the degree of U plus degree of V is less than beta minus 1. So Bernstein in a paper on random order streaming matching proved that the size of the maximum matching of H union U is larger than two-thirds of size of the maximum matching of G, and also the max degree of U is less than or equal n to epsilon square. So the max degree of this subgraph U is small, and also its union with H contains a large matching. So by choosing beta to be some logarithmic factor, polylogarithmic factor, then we have that this union of H and U has a small max degree. So therefore, in the step 2 of our algorithm, we sample set of R vertices, and R is O tilde of, and the size of the R is O tilde of 1. And then we run the LCA algorithm to count how many vertices of R are matched and output our estimate, which is the ratio of the vertices that are matched over all the vertices that we sampled times n over 2. So because the max degree of the U and H is small, we can run the LCA algorithm fast, and the total running time of algorithm is going to be sublinear. Next, we show how we can beat the two-third approximation ratio. Suppose that the union of H and U does not contain a larger than two-third of the maximum matching of G. Then we can show that the union of H and U contains a two-third matching that is also far from being maximal. So for example, in our construction, if we consider the EDS of the construction and then the EDCS, the matching of EDCS can be SP vertices, edges between SP. So it means so if we add AA edges to this matching, it can be augmented to a larger matching that is better than 2/3. So all we need is to find those AA edges that are missing in the EDCS. So also note that our 2/3 algorithm has slightly sublinear pre-processing for sampling edges, and we have access to Oracle to check the matching status of a vertex. So we can check if it's a vertex or B vertex in O of n to 1 plus epsilon, because B vertices are matched to S vertices and A vertices are unmatched. So using these tools, how we can find those AA edges? This is all we need to beat 2/3. So we define this matching oracle of induced subgraph problem. The assumption is that there exists a hidden set A that's the size of the maximum matching of A is 1/3 of mu of G. So it contains a large matching. We have access to membership oracle for A vertices in a slightly larger than linear time. Our goal is to find to estimate a constant approximation of the mu of GA. So we don't need a good approximation ratio here. We only need some constant approximation to beat the 2/3. Also, it's interesting that this subproblem used in the follow-up paper to get 1 minus epsilon approximation in sublinear time. So this result is by Bhattacharya, and so on, right, as a follow-up work. So this subproblem is also useful for follow-up works and also used in our beating 2/3 algorithm. So our approach is to sample n to epsilon half set of n to 2 minus epsilon edges and construct a greedy maximal matching MI on each of those sets. There are 3 possible scenarios after sampling and constructing greedy maximal matching on those edges. The first case is that one of those MI contains a large matching of the induced subgraph of A. The second case is that in one of MI, both endpoints of a large matching of induced subgraph of A is unmatched. And the last case is that in all MI, exactly one endpoint of the maximum matching of the induced subgraph of A is matched. So we start to investigate all these 3 cases one by one. If one of MI contains a large matching in the induced subgraph of A, then this case is easily distinguishable because we can sample O tilde of 1 edges of each MI, and for each of them, we run the membership oracle to see both of their endpoints are in A or not. Then if one of them has a large matching, we can distinguish that. In the second case, both for a large matching of induced subgraph of A, both endpoints of those edges are unmatched in MI. Then because the maximal matching because we build a greedy maximal matching on those edges and we randomly choose the edges of the maximal matching, we can show that the max degree of the graph that is produced by removing the vertices of maximal matching has a low degree. So because of this bound on the max degree, estimating a constant approximation of those edges that has both endpoints unmatched can be done very fast by the result of the Behnezhad in Fox 21. So this case is also easy to distinguish. Now consider the case 3 that in each MI, exactly one endpoint of the maximum matching of induced subgraph of A is matched. So here we have M1 that, those green edges, dash green edges are the maximum matching, and for each maximum matching edge, and each MI, one of the endpoints of the maximum matching is matched with MI. So in this case, if we consider one of the maximum matching edges, it has exactly n to epsilon half incident maximal matching edges that are connected to outside of A. So we can sample n to 1 minus epsilon half vertices of A and remove their maximal matching edges that goes to outside of A. So we can sample these, for example, if we sample these two A vertices, and then we can remove their neighbors in the maximal matchings. So we can show that a constant fraction of the vertices outside of A are erased each time. So we can repeat this process until we end up in one of the case 1 or 2 in our in our algorithm. And because the size of the vertices that are not A are decreased each time with a constant fraction, then we can show that in constant number of rounds, we will end up in one of those 2 cases that are easily distinguishable, which results in our final theorem. So we have a lower bound that shows that for beating 2/3, we need at least n to 1.2 queries. Also, we have an almost 2/3 approximate algorithm for general graphs in a slightly better than in a squared time. And for bipartite graphs, we can also beat 2/3 in a slightly better than in a squared time. Now we show the approximation and time trade-off that we already have for this problem. So there's a result by Behnezhad that gets approximation guarantee in linear time. Another result by Behnezhad, Roghani, Rubinstein, and Saberi that beat half approximation in n to 1 plus epsilon running time. Also, the Volcker algorithm queries n square has n square query complexity and calculate the exact matching. With this paper and the concurrent paper, we have the lower one that shows the 2/3 beating 2/3 needs n to 1.2 queries. Also, we have an algorithm that beats 2/3 for bipartite graphs in a slightly better than in a squared time. And for general graphs, this paper and the work by Behnezhad, Kis, and Sanurak get 2/3 in a slightly better than a squared time. In a follow-up paper, Behnezhad, Kis, and Sanurak proved that there exists an algorithm with 1 minus epsilon approximation guarantee that works in a slightly better than a squared time. So in this paper also they use the matching oracle for induced subgraph as a subroutine to get this approximation ratio. So there are a couple of open questions. So is it possible to get 1 minus epsilon approximation in a faster running time? Now, with this recent paper of Behnezhad, Kis, and Sanurak, this can be done in a slightly better than in a squared time, but is it possible to get this approximation guarantee, say, in n square root of n, for example, or maybe faster or slower? Also, any algorithm with new trade-off between approximation ratio and running time is interesting. Also, a lower bound with new trade-off and approximation ratio is also interesting. For example, ruling out that 1 minus epsilon approximation is not possible, for example, in n root n or n to 1.8. Thank you so much.